To make those choices. And then my selfish ad, sustainable and repeatable. I'm a broken record about this because I really think it's the missing link. When you do this by design, it becomes your recurring process. It's not a special, wow, this is a really high-risk data set, maybe I should do it this time. It becomes your standard operating procedure, and it becomes so much easier because you're not doing it just because an audit's coming up. You're not doing it just because a breach happened. You're doing it because it's part of what your core business processes are. And then just one quick relationship that we've seen, governance and data optimization and security, they always go hand in hand. I am yet to see a client or a company in which the governance is incredibly mature, but the optimization of their data and organization of that data is not mature. They tend to go hand in hand because in order to govern and in order to use. More expensive. It's going to be 10 times more difficult because you're trying to go back into prior processes and figure out, man, I wasn't looking for this. Who's going to know if I do this? If you define these things up front, you've already got them documented, you already have SMEs who are thinking about it, you already have your products defined at the hand of these. If you realize that you're not doing something, well, we're doing that with the other products. So it's easy for us to figure out what the fix is. We're not doing something for the first time because someone came knocking on the door and said, what you do with attention right now? So I really hope that one big takeaway from this is the role of developers, analysts, and architects. Because right now, the current state of privacy is not being guided by the folks in this room. And that's a problem for me. That's a big problem for me. The legal department should not be telling you what you need to build. The legal department should be confirming for you that what you're building is good. And then if it's not, helping you to figure that out. I spend a lot of my days trying to bridge the gap between legal and between the technical side, which basically just speak Latin and take Latin maybe. It doesn't go comfortably. So bridging that gap between them helps take that responsibility and that burden and move it over to the right people. What are some things that are being done today? Because privacy is impacting organizations regardless of their size. There are a lot of different approaches. None of them are one size fits all, of course. You have centralized privacy offices that are really trying to govern things at a holistic enterprise level, and that's great.
登山マップとかないですか？
トレッキングマップでよろしいですかね。はい。
着きました。循環バスね。2時半、3時半、4時。あと1時間半しかない。
Whether or not that person gets an email. It's probably pretty simple, right? It's just a rule. But if I say, hey, so that machine learning algorithm, can you define exactly how it gave me that upper and lower bound? Why did that person not get covered in insurance? Because that was a risk score? Now we're getting a little dicier. And one, I don't know if I can answer that. And two, am I allowed to answer that? Can I peel back the curtain and show people that information? How would I even do that? What decision tree in this random forest algorithm made that decision that kicked it over the edge and said that person's not insurable? These are really difficult questions to answer. So we're talking about the complexity in algorithmic and logical methods. The moment of decision making is very, very important for regulators, but it's also one of the hardest things to pinpoint when it comes to detailed and in-depth machine learning and deep learning. So it is much easier said than done. Algorithmic. So the FTC Act, Section 5, talks about unfair and deceptive acts, but it doesn't look at it through the context of my machine learning model made that choice. I didn't look at that guy and see, oh man, I hate his t-shirt. I don't want to cover him. It's not something like that. It's not that easy. So identifying what was unfair, what was deceptive, is an incredibly difficult process and even more incredibly difficult to prosecute. And then distinct risks between between algorithm bias and the use of algorithms. So just because my algorithm might be fair, it might not mistreat the representative population, maybe the person who gets the result does something with that, and they interpret the output in a different way than was intended. So you've got two sides to bias. You've got the bias in the algorithm, and you've got the bias in the output of the algorithm and the use of that algorithm. The bias, I mentioned before, it can be unintentional, it can be intentional. Sometimes we think we know the knowledge very well, and we encourage things that may have had a person bias nested in it. Maybe I think guys named Jared aren't worth loans. I don't know, maybe I've had bad experiences with guys that have the same name as me, and I just don't want that guy to get the loan anymore. Wouldn't be great for me, but it also brings in a really weird bias that shouldn't be there. But even if I have the best of intentions, man, most people I know named Jared, they do not pay their loans back. That's not great. That's anecdotal evidence. It's real cute. But then on top of that, with machine learning itself, it's going to perpetuate that bias systemically. So it might have just been one person said something and made a decision, but then it got perpetuated as part of that model going forward. And it might not be silly or Jared, but it might be something that's much more harmful. And then that balance between competitive advantage and transparency. We want to tell consumers what's happening to the extent that we can, but we also can't peel back everything. We want to let our competitors know exactly what logic we're using. So it's a really, really tight balance between those two things. So the role of developers and engineers, domain knowledge is critical. When I've seen legal departments or privacy offices try and define risk, they often say, can I get the people who built the product in the room? Because I can read the law, but I don't know. Why did you do that way? I don't know, I was on a 26-hour workday and a lot of coffee. I have no idea. So doing these upfront through design is incredibly important, and having it be the people that are in this room who do those things, who can actually answer those questions innately with the domain knowledge is incredibly important. And then building new methods. Who's going to build? So then I don't need to go to your head later. I know what you were thinking. I know what data is being used. I know what the logic is. I know what the outcomes are. So we'll talk a little bit about some methods for that. So real quickly, in order to do the few risk in your data approaches, we have to look at the different types of data that we deal with. So of course you've got your PII, your personally identifiable information, full name, social security number. I have that. I know who you are. Those are very simple. Then you've got your quasi-identifiable information in orange there. Your age, your gender, your zip code. Your age doesn't get me who you are. But if I get your age and your gender and your zip and maybe a couple other things, I can probably get pretty close to you. Maybe 1 out of 5. And once we're 1 out of 5, you probably don't feel safe anymore. So once you're getting there, you call it quasi-identifiable. I can combine it with other things to get to you. Non-identifiable information, I would caveat this by saying it depends on the data set. So we've got country here. Let's just imagine that this is a data set of 1,000 people from the U.S. It's not identifiable. There's nothing different about this data set. Yes, if there was one person who was from Laos and I knew that they worked at this company where the data set was, then maybe it fits. And then 4, sensitive information, be it for other regulatory issues, be it because of health, or because of legal or religious. These are things that really need to be protected. So different methods here. So anonymity, diversity, and closeness, they're all very interconnected. They all build off of one another. None of them are perfect. They're all labor intensive. But they're ways to look at risk in your data and try and cleanse it a little bit so that you can at least reduce the attack surface, so to speak. So K-anonymity is saying, I want to make sure that my data set has at least K records of a certain group. I don't want this data set to have such a rare medical condition that only one person in the world has it, and if I show that medical condition, I know exactly who that person is. That's an obscure example, but it really looks at how you need to make sure that there's at least enough of a representative population that you're not giving a record away, that releasing that data doesn't become but there's no weaknesses, homogeniity attacks, background knowledge attacks, knowing about the data. Income diversity. So diversity is an extension of this. It really says, look at the equivalence groups amongst my quasi-identifiable information. If I group all the people with the same age, gender, and zip code, how different are they? Do I have many of them? Do I have 2 of them? Do I have 20 of them with this one medical condition, 1 with the other medical condition? Well, what is the diversity looking like? Maybe I need to remove records because someone's privacy is going to be at risk. It would be the same basic process, but you get to work against attribute inference there. And weaknesses, so it's very complex. You're going to have to look at every single group of QI and then compare it to your other information, which can be very difficult. And then moving to closeness, which is again a further extension of this. It's looking at how does the distribution of my data look versus the global distribution. So if I cleanse my data throughout, I say, oh man, I'm just going to take out everyone that's female. Well, great. The global distribution of other identifiable or sensitive variables probably just changed because I just completely changed the population. So now someone who wants to look at that data set can now attack it and know you've introduced some change. Here's how it is. I can reverse engineer it. So these are not perfect, but they help build up the wall. So now a couple ways to actually look at model prediction risk. So adversarial training is one. This is actually a way of saying, let's combine competing tasks. Say I've got something I want to predict Y, and then something I don't want to be used, Z. Let's say I don't want to predict. I want my model to ignore it. I want my model start to look for when I'm trying, I stop. Adversarial training is a way for us to do this. So you can actually prevent the recovery of that sensitive attribute, because as you go and predict things, there's actually a negative gradient being provided back as a signal through your algorithm that says, I'm going to look for this and I'm going to not decide based on data if I see a correlation here. So it really, and the contrapositive will also prevent someone from saying, oh, there's a lack of this Z thing here, so then my model must not be dependent upon it. So I highly recommend, for example, the code here. I'd love to walk through every line, but I don't have that kind of time. AI Fairness 360, it's fantastic. It looks at adversarial training and so much more in terms of different algorithms for seeking out bias, but this is just one popular example. Dynamic upsampling through VAE. So VAE referring to variational autoencoders. This one is actually great because it doesn't require you to know what those sensitive attributes are. What's happening here is that by using this encoder, it's actually looking for latent representations in what your model is defining as it trains. So then as it's training, it can look and see, oh wow, it's really pinging on race here. I'm gonna pump data back in to tell it to stop looking at that, or to look at it less, to weight it less. So I can actually have my model train itself to look for things that it's impinging on and stop doing it so much. So it's really interesting because you don't have to define what that column is. It's going to look and see where the latent representations are. So it really prevents the amplification of bias, because once you ping on that field, you can ping on it again and again and again, and then the model learns from that and it keeps doing it. So if you want to stop doing that, this is one way to approach that. Developed by a team at MIT and Harvard. It's actually very cutting edge. The only code that you'll find for it is actually in some MIT deep learning labs. I highly encourage you to go out. Got a link here in the presentation. Happy to provide to anyone. It is open source. Finally, differential privacy. So it was formalized mathematically by Cynthia Dwork and a team of researchers to understand how I create epsilon differential privacy. What the heck does that mean? That means how do I get some kind of certainty that you can't identify an individual? Well, how am I going to do that? Well, I'm going to pump random noise into what I give you back. So let's say you come to me and you say, I'm going to put in an epsilon value of 0.25, and I want to know what the mean grade is for girls between 14 and 16 in Missouri. Okay, well, I don't need to give you the data set of all those protected folks. I can actually pump some random noise in there, and it's going to be controlled, so I know exactly how much noise I'm putting in there. So that I can give you a useful upper and lower bound. So you don't actually have to see all that data. You actually ask a question. You have a limited amount of queries you can send, so you can't just brute force attack it. But I can give you an answer back that is both statistically useful and doesn't give you information about individuals. So I can learn about a population, the generalities, in a way that's statistically useful, but I don't have to know that Jared is male, religious, St. Louis. I don't have to know those things because I can learn in other ways. So there's some great code. Google really is leading the way in this. They actually released and open sourced some of their differential privacy code. I highly recommend you go and look at it. It's incredibly intuitive, very insightful, and it's really spreading that message that the more we do this, the more this becomes standard operating procedure, the better off consumers will be. So now we're getting into the qualitative piece. First I'm going to talk about model cards for model reporting. Model cards is something that was created by researchers at Google and in tandem with University of Toronto. It's a mechanism for getting insight into the models as they're being designed and then as they're being tested. So it looks at things like model details, what's the intended use. Multidimensional privacy analytic. So this was created by Deirdre Mulligan and a team of researchers out of UC Berkeley. And I love this as an add-on to model cards because what it actually does is it takes the qualitative data and makes it important. It breaks out privacy into different dimensions, so you can think about it as what's the theory behind it? What is the privacy that's being protected? Who is being protected? Why? By what are they being protected? And then you can think about harm. Ultimately, this is about quantifying harm. How do I figure out where it is, and how do I help prevent it? So by mashing together model reporting cards and the privacy analytic, you can get both a qualitative and a quantitative look at what you're doing, which is incredibly important. So if you think about this, we talked about a lot of different methods. I want you to see this as a life cycle. And if I could make this circular with as many words, I would have, because it really needs to be iterative, just like the agile development process is. You need to be able to do this in a way that's not going to take you 6 hours every week. It has to be something you can do during story grooming or during a retro. It has to be something that you can answer quickly and efficiently without slowing you down. So you prioritize the risk assessments. You implement the privacy risk mitigation in your data. You look at where risk resides in your data. You utilize the tools that we talked about to root out bias or to minimize the amount of information that you share in answering queries. You get key feedback from your stakeholders. Talk to the business. Talk to ML. But for consumers and how you address these things. So this is just really a lot of words for us to re-explain that, but the piece I want to get through is that the folks in this room are the ones best suited to do this. Right now they're being done by folks who need your help, and it has to involve developers, engineers, and data scientists, because without that, we don't get the kind of insights into what we're thinking when we define these algorithms, or what we're thinking when we include this data and exclude that data. It's incredibly important for us to keep this context, because without that context, we can't clearly define the risk. Thank you very much. I work at MIT in the probabilistic computing project. So today I'm going to be talking to you about some new programming constructs for probabilistic AI that we've been developing in our group. So suppose you're given some data like the image on the left, and you're asked to explain it. One explanation is that this is an image of a coffee mug, but there are lots of other explanations you could give at different levels of detail. For example, you could say that this mug is being viewed from the top. So on the right, the red icon shows the viewpoint of the camera relative to the mug. And this more detailed explanation could be a lot more useful than just saying that it's a mug. For example, if we're a robot, it could plan the sequence of grasping motions we need to do in order to grasp the handle. Now, we also give other explanations. For example, we could say it's an empty mug, or we could say it's a ceramic mug or a rose mug, and there are lots of different ways of explaining this image. But for now, I'm going to suppose that we're most interested in the 3D geometry of the mug and its 3D orientation relative to the viewer. So here's another image of the same mug. So what's the 3D orientation this time? Well, in this case, there's two plausible explanations instead of one. It's definitely being viewed from the side, and the handle is visible, but it could either be standing upright or it could be upside down. And both situations would have resulted in the observed image on the left. So a key feature of human common sense reasoning and probabilistic reasoning is the ability to consider multiple plausible explanations for the data. And in other words, we can be uncertain about things. And uncertainty is going to be a key recurrent theme in this talk. So here's one more image of this mug. How will we explain this one? Well, here we probably have even more uncertainty. So like in the previous image, this mug could either be upside up or upside down. But because the handle is blocked, we don't exactly know what angle the mug is at this time. So there's a continuum of different possibilities. So if we didn't assume this was a mug beforehand, actually, there's even more explanations we could give. For example, maybe it's some sort of hollow cylinder-shaped object, or maybe it's just a cup without a handle, or maybe it's a solid cylinder of some sort. So the set of possible explanations that we're willing to consider is one of the key types of assumptions that we bring to the problem. And we might also assume that some types of objects are more likely than others, right? So maybe hollow cylinders and strange solid cylinders are less likely in our environment than mugs and cups. So if you see this image, maybe you're more likely to think it's another cup than a strange hollow cylinder. So these are examples of probabilistic inference, which we can think of as generally plausible explanations of observed data. So I'm going to show you another example. Suppose we're in some environment that contains 3 trees and a large enclosure with a building. Now, suppose we see a person moving around in this environment. So on the right, each blue X is going to be a location of the person at some time point. So here they're starting at the bottom left at 0 seconds. And after 1 second, they move up a little bit. And after 10 seconds, they're located here next to the wall. So we want to explain this observed data. So let's make some assumptions. So first we're going to assume that they're trying to go somewhere. And the place they're trying to go is somewhere in this environment. So we also suppose that they know the environment pretty well, so they need to plan an efficient route before they start walking. So then the person's destination and their planned route is going to be our explanation. So our question now is, well, where in the environment is this person trying to go? So here are going to be a few possible explanations. They could just be going right where they look like they're headed. So the red dot is their destination and the gray line is their route. They could be going a little further. That's also a good explanation. Or they could be going inside this enclosure. That also makes sense. And they could be going anywhere inside the enclosure, really. Or they could be going across the other side of this area. So what makes these explanations more plausible or reasonable than the other points, like this one? Well, our assumption that the person is trying to be pretty efficient in their walking. So we're going to judge circuitous routes like this one to be less likely. So the image on the right now shows an aggregation of all these possible destinations that could explain this data. And again, this is an example of uncertainty. We can't be exactly sure where they're going, but we think that some areas are more likely than others. So lots of other problems can be framed this way. So for example, if we see a sentence, I see a man with a telescope, there's 2 possible meanings at least. One could be using a telescope, I see a man, or I see a man who has a telescope. And these correspond to the composed truths for the sentence. And we can also use probabilistic inference for more standard statistical problems, like interpreting some time series data. So here we see some data on the left, and we might say, well, I think this is a sinusoidal oscillation, it's good, and there's also a linear trend, and maybe there's something like some pattern going on in the tracks of the sinusoid, but I can't be 100% sure that that's real, but it's being some noise. So each of these examples, there's some data, and then there are assumptions that go with the problem. Yeah.
100円のないですか？
はい。
100円の商品ない。
100円の商品はそうですね、ちょっと置いて。
安いのどれですか？一番安い。
安い100円の商品って何ですか？
どうぞ。
ああ、どうぞどうぞ。
どうぞどうぞ。
どうぞどうぞ。
あ、まだ決めてないんで。
私も決めてない。そうそうそう。ブレンドにして、こっちにするかな。でも甘いのな。
じゃあこのクッキー、
はいこちらです。